I'm not going to ask you to tell me what it is. Has anyone found the first eigenvector? Okay. I feel like this one might feel a little bit tricky. I think one of the things has to be 0. I might be wrong though. Maybe I could be wrong. This first eigenvector is one of those rare situations where the first row doesn't help you out, right? Doing 1 times x plus 0 times y equals 1 times x just tells you x equals x, which isn't helpful. The second row is what we need to focus on here, which tells us 4 times x minus 1 times y equals 1 times y. And then we can get a relationship between x and y. So kind of run out of room here. Let me go back over here. So there's the relationship y equals 2x. And here's the kind of standard choice of eigenvector. I would pick 1 for x and 2 for y. Has your teacher mentioned anything about eigenlines yet? Or Nullclines? Okay, it's all right. So, questions about what I've done before we look at the other one? Everyone, just as a reminder, that when you have a matrix that's diagonal, like, sorry, not diagonal, triangular like this, so we call a matrix triangular if everything above the diagonal is 0, if everything below the diagonal is 0. So this one's definitely lower triangular because everything below the diagonal is not 0. Everything above the diagonal is 0. This matrix, which is lower triangle, the eigenvalues are just the things on the diagonal, 1 and -1. You can also still do the long way, but you don't want to do the long way, right? You want to be like, oh yeah, I know the eigenvalues here are definitely 1 and -1. For lambda equal to -1, let's find the eigenvector. So we're going to solve. So we're going to call this eigenvector V2. And we're going to solve A times V2 equal to -1 times V2. So that's going to be same matrix 1, 0, 4, -1 times the eigenvector, which we're trying to find, equal to -1 times the eigenvector that we're trying to find. And here we actually get a lot from the first row. The equation from the first row is 1 times x plus 0 times y equals -1 times x. And if x equals -x, there's only one thing x can be. Somebody tell me. -1. Does -1 equal -1? That's the only number that's its own negative. It is 0. You're going to see this. This is going to come up not infrequently, maybe not like super frequently, but frequently enough that when you see something equal to a different multiple of the same something, you're always getting that something equal to 0. So like just as an aside here, if you end up getting it, oh my gosh, can I grab a pen? Maybe. If you see an equation like x equal to 5x, or 2x equal to -x, or 3x equal to -3x, all of these are going to result in x equal to 0. Because the only number that's a different multiple of itself is equal to 0. Any other number, if you multiply by something else, you get a different result. So x equal to -x gives us x equal to 0. You can also do the work, right? In each of these instances, I can totally like add x over here and get 2x equal to 0 and then x equals 0. Or here I could subtract 5x and get -4x equal to 0 and then divide by -4 and get x equal to 0. But I don't want you to have to do that work, right? I want you to be able to see, oh yeah, I know we're going to get x equal to 0. If x equals 0, What does that mean for y? Y gets to be whatever you want it to be. We're going to pick 1. So my eigenvector here is 0, 1. And again, I should be more specific. Y gets to be anything you want it to be except for 0. Because 0, 0 is never an eigenvector. I'm going to say that like every time. 0, 0 is never an eigenvector. All right. You got it right. Oh, question.
If we multiply the 4 by the x and -1 by the y, and then the -1 by the y, like how would that?
So let me ask you, if you were just solving this, what would cancel?
The y.
Right. The y's cancel. What are you left with?
4x equals 0.
Right, which means x has to be 0. And then we're left with the same situation. If x is 0, we just make a choice for y, and the choice we're going to make is 1.
So we can have our x value as 1.
Nope, we can't have x be 1.
Oh.
We've specifically said x has to be 0. Right? And my eigenvector is reflecting that. The x part is 0. The y part is 1.
What if we solve the y first, though?
So like what you're saying, what if we did this one first?
Yeah.
So if we do this one first, we're still going to get x equal to 0. So it's not that the first equation gives us x and the second equation gives us y. It's that the first equation gives us something. Sometimes the second equation gives us something, and usually it's like y equals something with x or x equals something with y. Like over here, right? We did the first equation. Actually, no, we did the second equation for this one, right? Because we got x equal to x, which wasn't helpful. And then the second equation gave us 4x minus y equal to x. And so we solved and we got y equal to 2x. That's not giving us x or y specifically. It's giving us a relationship between them. So we know that whatever x is, y has to be twice it. So the eigenvector is, oh, x is something and y is double it. But yeah, so really, typically this is what we get. Sometimes you get something where x is 0 and then y has to be 1. Or flip it where y is 0 and x has to be 1. So now that we've got our eigenvalues and our associated eigenvectors, and it is important to make sure that you keep them in like as pairs. So our lambda1 is 1 and the eigenvector is 1, 2. And our lambda2 is -1 and the eigenvector is 0, 1. 0, 1, 0, 1. Okay. So now we're going to write the general solution. And oh, question. Right. Yes, you can pick y equal to 3 or -7 or any non-zero number you like. It'd still be right. It'd still be an eigenvector. So actually, let's actually explore that for just 1 second. So let's say instead of picking 0, 1, we pick the eigenvector 0, 8 because I like the number 8. Then it should still be true that the matrix times our eigenvector is equal to the eigenvalue, which is -1 for this particular eigenvector times the eigenvector. So let's check it out. My matrix was 1, 0, 4, -1, and multiply it by 0, 8. And am I going to get -1 times 0, 8? You bet I am, because 1 times 0 plus 0 times 8 gives me 0. And 4 times 0 plus -1 times 8 gives me -1 times 8. So as you might notice, it doesn't actually matter what number I put here, right? Because when I do the math, the top row is 1 times 0 plus 0 times I don't care equals -1 times 0. Well, that's going to work out because 0 plus 0 equals 0. And in the second row, 4 times 0 plus -1 times we really don't care as long as it's not 0 equals -1 times the same I really don't care. Oh, but that's 0. So of course this is equal to that. So really when we talk about eigenvectors, any multiple of an eigenvector is also an eigenvector for the same eigenvalue. So while we usually make the standard choice of 0, 1 here, you can make any non-zero choice you wanted. But you should choose 0, 1 because it's going to be what people pick. Likewise here, any multiple of this eigenvector is also an eigenvector. 2, 4, -1,000, -2,000, right? Lots of different choices. And so it's also true that the matrix A, 1, 0, 4, -1 times the eigenvector 1, 2 should equal 1 times the same eigenvector 1, 2. And it does. 1 times 1 plus 0 times 2 is 1. 4 times 1 plus -1 times 2 is 2. But I could have made other choices there, right? If I had picked the eigenvector, oh, sorry, yes. If I picked the eigenvector, say 3, 6, I'm going to get 1 times 3 plus 0 times 6. And I get 4 times 3 minus 1 times 6, which is 6. Oh, yeah, that's also an eigenvector. So any multiple of an eigenvector is also an eigenvector for the same eigenvalue. And that's why we talk about the eigenline, because the line that contains your eigenvector contains every eigenvector that's a multiple of it. It's just a direction. You say, oh, everything in this direction doesn't get, so the whole point of an eigenvector is that when you multiply the matrix by it, it doesn't change directions. It might change length, or it might, or I should, you could say this one's changing direction because it's becoming the opposite direction, but it's still like on the same line in the kind of same direction. But the whole point of an eigenvector is multiplying the matrix by it doesn't change the direction it's going in. Okay. Don't worry, we're gonna see this in a minute when we talk about the direction field or the phase plane, sorry. Let's write the general solution. And they really can't strongly enough say you should memorize the formula for the general solution, which is C1e to the lambda 1t times V1 plus C2e to the lambda 2t times V2. That should be in your head. And then we're just going to write all the things. I should be a little more specific. That's what x of t, y of t is equal to. That's our solution, our general solution. So we're going to have the x of t, y of t is equal to, let's see, so it's going to be, we don't know C1 and C2, right? Those are the things that make it general. When we solve for those, that's when it's particular. So it's going to be C1e to the 1 times t times the first eigenvector plus C2e to the -1 times t times the second eigenvector. And then we can solve very easily here. So we want to find the particular solution. That's when I'm going to use my initial conditions, which I often abbreviate as IC, which were x at time equal to 0 equals 2, y at time equal to 0 equals 10. So I'm just going to plug in 0 for time, and all the plugging in 0 for time is really going to do is make e to the e term go away. E to the 0 is 1, e to the 0 is 1. That's what we're always going to get when we're plugging t equals 0. The way we multiply the vectors, like the matrix by the vector over here, is rows by columns. So it's this row times this column. 1 times 1 plus 0 times 2 gives me 1. And it's this row times this column. 4 times 1 plus -1 times 2 is 4 minus 2, which is 2. That's how the vector, that's how the matrix multiplication works. So I'm now going to have x of 0, which is 2, y of 0, which is 10, equal to C1 times e to the 0, which I don't want to write because it's just 1, times 1, 2, plus C2 times, again, e to the 0, 0, 1. And it's always nice, if we're lucky, if you have a 0 in one of these spots. So if you have a 0 in one of those spots, it's really easy to solve for one of the variables right off the bat. Can anyone tell me, just by looking at this or write in the chat, actually show me on your fingers if you can see, what does C1 have to be equal to? You only need one hand to show me on your fingers. Has to do with the fact that there's a 0 here. Yeah, I see. Okay, I'm seeing more fingers. Yes, it's a peaceful day. Yes. It's 2, right? Because C1 times 1 plus C2 times 0 has to equal that part right there. So we automatically can be like, oh, C1 has to equal 2. There's no other choice. Now, if all the things are not zeros, then it's more work to figure out what the constants are. But then knowing that C1 equals 2, we can also find C2 pretty easily, because now we're going to say, okay, that's 2. And then 10 has to equal 2 times 2 plus C2 times 1. Well, that means C2 has to be 6. So it's always nice if one of those things is 0. It doesn't happen a lot of the time, but it does happen some of the time. You guys are asking great questions. Don't hesitate to ask questions if you have questions. Here's our particular solution. It is x of t, y of t equal to C1 times e to the t times the vector 1, 2 plus C2, which is 6 e to the negative t times the vector 0, 1. Excuse me. Somebody might, on occasion, ask you like, well, what's the behavior of x? Like the first thing as time goes on, and then you could actually write out just what x is. So we're not, this is how you should write the answer, but it's also fine to say, whoa, x is just the first row. So x is 2 e to the t times 1 plus 6 e to the negative t times 0. That's just 0. So x of t is 2 e to the t, and y of t is the second row. It's 2 e to the t times 2 plus 6 e to the negative t times 1. And I would probably rewrite that as y of t equals 4 e to the t plus 6 e to the negative t. Usually people are not asking, well, that's not true. I take that back. People ask for that sometimes. Sure, what else do we want to say about this? All right, so let's talk about what's happening. So, as time goes on, what's happening to the population size for x? Is it growing or is it not? It's definitely growing, right? As time goes on, this e to the t gets larger and larger and larger and larger. So as time goes on, the population for x gets larger and larger and larger. What about for y? Well, y is 4 e to the t plus 6 e to the negative t. This part's going to go to 0, but this part's going to get larger and larger and larger. So it's also going to get infinitely large. That's a good question. I like that question. So the reason it's not is, so we're not so much concerned with the coefficient as the part that's changing. So the idea here is that 6 e to the negative t, well, I'm going to rewrite this as 4 e to the t plus 6 over e to the t. So it's not that this is balancing that out. 6 over e to the t, as t gets larger and larger, e to the t gets very, very large, and 6 divided by e to the t gets very, very small. So this is going to 0, but this is going to infinity. Yeah. And then, yeah, we should do that. So, yeah, so let's talk about sketching the phase plane.
Is that where we do like x1 and x2 for the?
That's a different thing. That's so we can also sketch the, what do you call those things?
How does that work? Like, what is x1 and x2?
Well, so typically in a lot of these examples, x1 and x2 represent like populations of species or amounts of stuff is a more general understanding. So x is the amount of stuff at time t, and y is the amount of stuff at time t. So not surprisingly, we already know this, but looking at this equation, we can see that, okay, at time equals 0, x of 0 is 2 e to the 0, which is just 2. And y of 0 is 4 times e to the 0 plus 6 times e to the 0, which is 10. Which were the conditions we were given, which is how we solved things in the first place. And then we can see that both of these are going to grow, right? At time equals 1, which I know is not an excellent number to plug in, x of 1 is going to be 4 times e to the first. And y of 1 is going to be, oh, sorry, that's a 2, not a 4. Apologies. I'm looking at the wrong equation. And y is going to be 4 times e plus 6 divided by e. And I might actually have gotten smaller. No, it's still a little bit bigger than 10. All right, so the idea is that you can plot both of these things. You can graph both of them. We'll come back to sketching the phase plane. You can, I always forget the word too. We can write the individual solution curves. I'm really just looking at the equations, right? I know what the graph of 2e to the t looks like. At time equals 0, it's going to be 1. And then it's just got the usual kind of exponential shape. It starts there, right? We don't have anything to the left of t equals 0 because it doesn't typically make sense to consider negative times. And then we can also graph the solution curve for y. And y is going to start at 10. And actually, I don't know exactly how this works. I don't know about that. Let's look at Desmos. Desmos is a great tool for graphing things. I'm curious. So if we graph y of t, I need the slider for t, equal to 4e to the t plus 6e to the negative t, not to t. Oh, I don't need those. Okay, fine. I always forget. Thank God. Where'd it go? Is there no graph? No, probably it's not zoomed out enough. There we go. So we zoom in now. Okay, it actually does dip a little bit at first. So if I was graphing that, I would be like, all right, I'm going to dip a little bit, but then eventually it's going to do this kind of deal. And again, we don't care about anything to the left of 0. So that's what's happening for the populations, right? Population of X is just growing from the get-go. The population of Y sinks a little bit, but then it picks up real fast. Okay, so I want to talk about how you would draw the phase plane without actually using a tool. And there's kind of 2 types of lines that are important in doing this. One type of line are the eigenvectors. I should say the eigenlines, really. Eigenlines. And then we also have nullclines. What are these things? Well, in this particular problem, the eigenlines, you already know. The eigenlines are just the lines that include the vectors. So our vectors being, I forgot, 1, 2, 1, 2, 1, 2. And then where's my notes? Yeah, 1, 2. And 0, 1. So I want the line that includes 1, 2. Well, you know what's actually easier to do? It's easier to go back and look at the work we did finding the vector and be like, oh, we got the vector by this. That is your eigenline. Y equals 2x is the line that includes that vector, right? Because that vector 1, 2 is definitely on that line. So the eigenline is the line y equal to 2x. And here, the eigenline is the line, brain, x equal to 0, which again is the equation we used to get the eigenvector. So I'm going to start trying to draw this thing. So here's what's true about the eigenlines. And let me make sure I draw this in a not super terrible way. Yeah, I can draw this not terribly. I want to go over 1 up 2. And normally we would draw lines that putting arrows at the end. You actually don't want to do that here because the arrows are going to represent the vectors in your direction field in your phase plane. So here's what's great about eigenlines. On an eigenline, any point you pick, the vector that would be in the vector field goes in exactly the direction of the eigenline. Let me show you what I mean. Here are the equations we started with way back when. dx dt equal to, was it x, I think? Yeah, dx dt equal to x, and dy dt equal to 4x minus y. So let's see what happens if I plug in the point 1, 2. So if I plug in 1, 2, dx dt is going to be 1, dy dt is going to be 4 minus 2, which is 2. Oh, I'm exactly going in the direction of 1, 2. And that's true for any point on the eigenline. If I pick something like, 2, 4, I'm going to get literally the derivatives being 2 and 4. So the point is that when you're on the eigenline, all the direction vectors move in the direction of the eigenline. And there's something else that's nice about this. If the eigenvalue associated with the eigenvector is positive, which it is here, the vectors move away from the origin. And that should kind of make sense considering what we talked about last time, because we saw that when the eigenvalues were positive, we had instability, right? We were growing, we were moving away from 0, 0, which is the only point of equilibrium. On the other hand, for this eigenline, which is a little bit less nice to deal with, it's the line x equals 0, which is just this vertical line, which is associated with lambda 2 equal to -1. We're going to see that whatever value we pick here, the eigenvector is going to be pointing, or I should say the direction vector is going to be pointing towards the origin. So if I pick, for example, the point like 0, 1, dx dt is going to be 0, so there's 0 change in the x direction. dy dt is going to be 0 minus 1, which is -1. So I'm going to be pointing in the 0, -1 direction, which is back down. Or if I pick the point like, 0, 7, I'm going to get 0 and 0 minus 7, which is -7. So way up here, I'm going to be pointing down. Whereas down here on the eigenline, if I pick something like 0, -2, dx dt is still 0, dy dt is 0 minus -2, which is pointing upwards. So eigenlines are great. The vectors point in exactly the direction of the eigenline. And they point away from the origin if the eigenvalue is positive. They point towards the origin if the eigenvalue is negative. If the eigenvalue is 0, we hope it's not 0. Usually, I don't think Rademacher usually talks about the eigenvalue being 0. There's definitely one professor who's not who you have who kind of focuses on it, which I think is too bad, but whatever. Not something we have to worry about. Okay. The other lines we typically worry about or concern ourselves with are what are called nullclines. And those are where the derivative of one particular direction is equal to 0. So I'm going to look back at my original equation. And I'm going to set each derivative equal to 0. So I'm going to set dx dt, which is equal to x. I'm going to set that equal to 0. Actually, let's not do that one first. I'll do the other one first because it's a little more interesting. And we're also going to set dy dt, which is equal to 4x minus y equal to 0. And kind of unlike when we were finding critical points for functions of two variables, and we had to gosh, I'm really kind of burpy, sorry. We had to simultaneously solve the partials equal to 0. We do not have to simultaneously solve these. We already know what the simultaneous solution is. It's the origin. If the origin is the only place that is a solution to both these things equaling 0. We don't care. I mean, we care about that, but like, that's not the point. The point here is I want to find the curve or line that solves this. Well, that's not that terrible. I'm just solving, or I'm just getting y equal to 4x. So y equal to 4x is my Nullcline. So I'm going to try and draw this. I should have drawn this a little more exaggerated. Oh well. Such is life. Sometimes you don't make all the choices you want to make the right way. Oh, come on, be straight. Oh, I don't want that arrow there. Ignore the arrow. The arrow is garbage. Yeah, this could be better. So this is the eigenline. Y equal to 4x. So here's what's true on this line. On this line, dy dt is equal to 0. Dy dt is the change in y. So that means all of the arrows on this line should have no vertical change. All the change along this line should be horizontal, meaning the arrows are either pointing completely to the right or completely to the left. There is no up or downness to the arrows. So let's pick a point. Let's say I pick the point, an easy one like 1, 4. If I plug in 1, 4, dx dt is going to be 1, so it's pointing to the right, and dy dt is going to be 4 minus 4, which is 0. So it's not pointing up or down. So at 1, 4, it's pointing to the right. And any other point up here, it's also going to be pointing to the right. And then down here, if you pick a negative, so like the point -1, -4, you're going to be pointing to the left because dx dt is going to be a negative number and dy dt is still going to be 0. So all the arrows down here point to the left. Okay, we're almost done. The other Nullcline is not that interesting because if we set dx dt equal to 0, we get x equal to 0, which is already this eigenline. But that's okay, right? We're still getting, it's still correct. Because on this line, it should be true that dx dt is 0, meaning there's no x direction change, it's all y direction change. So there's no arrows pointing left or right, they're all pointing completely vertically, which they are, right? They're all pointing either straight down over here or straight up over here. So these are the lines we typically consider when we're graphing a thing. And see, the thing about this now is that we can kind of see what the behavior of this system looks like, because you get pushed kind of in the direction of these things. So if I start here, I'm going to move kind of this way. If I start up here, I'm going to get pushed down and to that way. If I started in here, I would get pushed kind of that way. If I started over here, I would get pushed kind of that way. So the arrows kind of tell you which direction you have to go. It's not perfect, right? Certainly graphing something like this is a process, but it can give you an idea of, okay, if I started at the point, my initial condition 2, 10 over to up 10 puts me like kind of way up here. I'm going to end up doing this kind of deal, right? I mean, it's going to be like that kind of deal because I'm in this section here where I'm getting pushed that way. Let's actually look at the direction field or the phase plane. Where'd you go? I hid you from myself. There we are. So there it is. Let's make it bigger. So dx dt is x and dy dt is 4 times x minus y, which is what I had, right? Yeah, 4 times x minus y. And you can hopefully kind of, now, the nice thing, if you do decide to take the time to download P-Plane, one of the cool things that P-Plane actually some functionality has is that you can have it graph the Nullclines and the Eigenlines for you, which is kind of neat. I can't put those on here because I can't, there's no functionality that way. But we can still kind of see, oh yeah, look, if you look along this line here, everything's pointing down, everything's pointing straight up. if you were actually on the line. But as soon as you kind of perturb a little bit to either side, you start going in different directions. And then it's slightly harder to see. But if you look in the direction of y equals 2x, you can kind of see, oh yeah, we're just kind of, right? It's not super easy to see, but you can kind of see, oh yeah. Maybe if I made my window a little smaller. Sure, let's do that. Maybe less arrows. Oh, that's not enough arrows. It's terrible. Take it back. Cool. So you can see if we go over 1 and up 2, we're just kind of going straight in that direction. We keep going that way. I should say you can see, you can kind of see, right? I'm like, can I really see that there? I'm like, over 1 and up 2. So, are there questions at this juncture? It's okay if there aren't. But it's certainly okay if there are. Why might we care about these things? Because they help us kind of see what things look like. What I should be saying here is that this system, this system is a saddle. So here, before we saw last time, we saw a stable node, AKA a sink. We also saw an unstable node, which is known as a source. And now we're seeing a saddle, which is in some direct, like from here, we're kind of going in and we're getting pushed out. Along this eigenline, we're going in towards the equilibrium. And along this eigenline, we're getting pushed away from it. So this is generally considered to be an unstable system because unless you start literally on the eigenline where you're getting pushed towards it, you're going to get pushed away from it. So this is unstable. It's an unstable, and it's a saddle. Let's see what time is it. Okay. Yeah. Sure. We'll come back to that. We'll come back to that. So I think I don't remember how much this particular feature really talks about all this eigenline, nullcline stuff. So I don't want to like inundate you with it, but I do want you to not have not seen it. So let's talk about classifying stability. So I feel like that's definitely something where everyone's going to end up eventually. Well, not everyone, they're all in the same class, right? But let's talk about how to classify the stability of a system of linear differential equations. There are 6 possibilities in general. 3 if the eigenvalues are real, and another 3, which we're not talking about today, where the eigenvalues are complex. So there are 6 possible situations. And then for real eigenvalues, there are 6. That's 6. There are 3 possibilities. We have seen each of them. And this is kind of why I talked about the eigenlines, because the eigenlines really kind of help you see it. So here are the 3 possibilities. 1, if both eigenvalues are positive, then, well, here's what we have, something that look kind of like this, where you have maybe an eigenline here and an eigenline there. And if they're both positive, you're getting pushed away from the origin, right? You're pushed in the direction of the eigenline. So let me ask you all, are we getting pushed towards our equilibrium or away from our equilibrium? Away. And if we're getting pushed away from the equilibrium, we are unstable. So if both of them are positive, it's an unstable system. And specifically, it's called a source or an unstable node. Those are the two different names. And what this ends up kind of little words. What ends up, I just can't talk anymore. What this ends up kind of looking like is, you've got things like if you start here at this initial condition, you kind of end up going that way. Or if you start here at this initial condition, you kind of end up going that way. And wherever you start, you end up getting pushed away from the origin. And you might have things that look more like you might do something like that. That could also happen. But you're always moving away from the origin. An example, an easy example of a system that has this is something like dx dt equal to 2x, dy dt equal to 2y. It's not a very interesting example, but the matrix for this would be 2, 0, 0, 2. And it's actually really, really easy to find the eigenvalues. What are the eigenvalues? They're both 2. And the eigenvectors are 1, 1, and 1, negative 1. I know I didn't show the work for them, but that's what they are. If you think about it, right? This matrix times 1, 1 is 2 plus 0 and 0 plus 2. Oh, that works. That's 2 times the vector. And the matrix times 1, negative 1 is 2 plus 0 and 0 plus negative 2. Oh yeah, each of these eigenvectors, when multiplied by the matrix, got multiplied by a factor of 2. So there's my eigenvector 1, 1. There's my eigenvector negative 1, 1, or my eigenlines. Y equals x. Y equals negative x. And because I think it's good to see these things in actuality, if we actually look at this, I remember the times 2 times x. Let me just actually have the standard kind of window. Did I get an x there? Is that something else? I'm having trouble seeing there. So everything's going out, right? It is definitely a source at the origin. Everything is moving away from it. It's the beginning of all things. And if, I forgot you can do this, right? If we have an initial condition, like let's say our initial condition was, I don't know, 2, 1. Oh, look, yeah, we're definitely moving away in that direction. I like looking all over this kind of thing. This one, right, in this one, unlike the previous examples we saw last time, the other example is kind of like curved kind of away a little bit. These ones are very much moving, like it's not exactly straight, but you're moving, no, it's pretty straight. I think we're moving exactly in straight lines kind of away. That kind of happens sometimes. That's one possibility. Another possibility that we've seen, I mean, we've seen all the possibilities, is that if both eigenvalues are negative, then when we have something that looks like this, oops, wow. There's our eigenlines again, but not everything is pointing inwards. So we have what we call a stable node, which is also known as a sink. Yeah.
When you use like sink and source, are you referring to a specific point or just
Yeah, you're kind of saying that the equilibrium point, which is the source, which is the origin, is the sink or the source. So here, so what we're classifying is we're actually classifying, I should, you asked a great question. Yeah, I can make it for sure. I should go back and qualify here. So 1 second, I should say the unstable equilibrium. And it is a source or an unstable node. So yes, we are talking about the equilibrium point. And for all of these examples, right, for all these examples where it's a linear system of differential equations, where it's just a multiple of x plus or minus a multiple of y, the origin is always the only point of equilibrium. That's going to change eventually, but for now, it's super nice, right? The origin is the only one. So here, yeah, we're saying that the origin is an unstable node or a source. And here, and I apologize for reading that. We have that the origin 0, 0 is a stable node or a sink, right? And I should just point out, right, this is the point of equilibrium. Let me remind you, just so everyone is super clear on this, the reason that's true is because, right, if you're writing a different set of different equations, like I'm going to say dx dt equal to 3x minus 4y, dy dt equal to 2x plus y, right? If this is your system, I don't know if these actually give you negative eigenvalues, I just made it up. But the whole point is that if you're trying to find where you have equilibrium, you're trying to find where there is no change. And the only place where there's no change is where the derivatives are both equal to 0. And the only point where both of them are equal to 0 at the same time is 0, 0. So that's why the origin is our equilibrium, because it's the only place where nothing is changing. And then the last one, the last type of real eigenvalue situation is if one of the eigenvalues is positive and one of the eigenvalues is negative, then the equilibrium 0, 0 is called a saddle, which is considered unstable. And then just a point of clarification, all right, we could get stability if we start at an initial condition on the eigenline associated to the negative eigenvalue. So picture-wise, if here's your first eigenline, and here's your second eigenline, and the first one has a positive eigenvalue, so we're pushing out on that. And the second one has a negative eigenvalue, so we're pushing in on that. If your initial condition happens to start you right there, great. You're going to end up going towards the origin. But if you even start just a little bit off of it, then yeah, you're pushing that way, but you're also getting pushed that way as well. So you're kind of going, oh no. What happens? No, it's just called a saddle. It's never a sink or a source. So there's 3 different things for when the eigenvalues are real. You can have a sink, you can have a source, or you can have a saddle. Those are the only options. There's like one other super lame option when like one or both of the eigenvalues are 0. If that comes up, let me know. Typically people don't cover that, so I wouldn't worry too much about it. But if it does, we can talk about it. It's kind of super funky, but not that terrible once you know how it works. Let's see. So the nice thing about this is you don't have to do a bunch of work to know how to classify the system. Meaning, let's say our matrix was, let's say our system was dx dt equal to 4x plus 2y, and dy dt equal to negative 5x plus 3y. And we want to classify the equilibrium point, which we know is the origin. It can't be anything else. I should just stress, eventually that's not going to be true, right? But as long as it's multiple of x plus multiple of y, multiple of x plus multiple of y, as long as they're linear systems of differential equations, the origin is the only equilibrium. And then, okay, I'm going to qualify that in just a second because that's not 100% true. Then we can just find the eigenvalues of the system. So here's our matrix, 4, 2, negative 5, 3. And you can either find the eigenvalues in the determinant of 4 minus lambda, 2, negative 5, 3 minus lambda. I don't know if you guys have seen this notation. When you write a matrix, instead of writing big brackets, you write big vertical lines. So it kind of looks like a big absolute value. That notation means determinant. So this means the determinant of the matrix A. If you're calling this matrix A. And it's just convenient notation. It's better than writing determinant parentheses of the matrix. And then that's going to be 4 minus lambda times 3 minus lambda minus 2 times negative 5, which is going to be, let's see, equal to 0. And then we're going to have lambda squared. Minus 4 lambda minus 3 lambda is minus 7 lambda. 3 times 4 is 12. I'm a little worried about this one here. It looks like it's going to be gross. Did I make a mistake? Did I make a mistake? I did make a mistake. It's okay. We can fix it. The matrix is supposed to be negative 4 here. Sorry about that. Luckily, it's an easy mistake to fix. Except at this point for my negative 7 lambda. So really I should have lambda squared minus 3 lambda plus 4 lambda, which is plus lambda, and then minus 12 plus 10, which is 0. And that's going to give me lambda squared plus lambda minus 2 equal to 0. And this does factor. I should warn you, eventually we're going to see things that don't factor, especially when the eigenvalues are complex, meaning imaginary, right? They're definitely not going to factor if they're complex eigenvalues. Here we get lambda equal to negative 2 and lambda equal to positive 1. So that means our origin is what? Sink, source, or saddle? Saddle. Oh. I want to kind of point out, because definitely your teacher does, I was looking at his notes, he definitely does talk about the trace and the determinant of the matrix. So another way we could have found the eigenvalues here is to remember, well, so how do I want to say this? Yeah, I really do want to say it this way. So here's an alternative way of doing this. This comes up, and there is a reason to do this. It is nice. I'm not just doing this for the sake of doing it. Right? There's like, it's actually useful to do this instead. So if we look back at this matrix, what is the trace of that matrix? Well, the trace is the sum of the diagonals, which is what? People on Zoom? It is definitely -1, right? It's -4 plus 3, which is -1. And the determinant of the matrix, which we often use the symbol capital delta for, is what? Well, okay, it's -4 times 3 minus 2 times -5, which is -12 plus 10, which is -2. And the idea that we've seen, that I did say before, but I'm going to say again, is that when you write out this polynomial after you've simplified it, it's always going to be lambda squared minus the trace times lambda plus the determinant. That's always true. My trace is -1. I had lambda squared minus -1 times lambda, or lambda squared plus lambda, minus 2. And minus 2 was the determinant, so plus -2. Why is this useful? Well, okay. This is always what we're going to get when we find the determinant of A minus n. So I'm going to say this again in more words. The determinant of A minus lambda I equal to 0 always becomes the equation lambda squared minus the trace times lambda plus the determinant equal to 0. Those are literally the same equation. I know they look very different, but they're literally the same. In the particular example we're doing, I'm saying, okay, the determinant of -4 minus lambda 2, -5, 3 minus lambda equal to 0. I forgot the determinant. That is the same as lambda squared minus the trace of the matrix times lambda plus the determinant of the matrix equal to 0. They're the same. I know they look wildly different, kind of, but they actually are the same. And trust me, I'm getting to the point. The point is that if we know that this is always the equation that we're trying to solve, you could throw the quadratic formula at it very easily. So I'm going to say, all right, if I'm trying to solve this, where my variable is lambda, right? You might prefer to think of it as x squared minus the trace times x plus the determinant equal to 0. And either way, what are my A, B, and C if I'm going to use the quadratic formula? What's A? 1. Right? Where we're thinking like ax squared plus bx plus c equal to 0. So A is 1. Okay, what's B? It's almost the trace. It's the negative of the trace, right? Because it's got to be. So I should probably write this as lambda squared plus the negative of the trace times lambda plus the determinant. And now what's the C value going to be? It is the determinant. Okay, so now we can use the quadratic formula and say, well, the solutions are going to be negative b plus or minus the square root of b squared. You could write the negative trace squared, but you don't really need the negative there because a negative thing squared is the same as a positive thing squared. Minus 4 times a times c all over 2 times a. So sometimes it's going to be more convenient to do this. A lot of the time it's going to be more convenient to do this. For this particular example, which I know we've kind of harped on for a while, for A equal to this matrix, -4, 2, -5, 3, the eigenvalues are, okay, well, we said the trace was -1, the determinant was -12 plus 10, which is -2. We can find the eigenvalues as -1 plus or minus the square root of the trace squared minus 4 times -2 all over 2, which is not terrible. It might feel terrible at first. But we get -1 plus 3, which is 2 over 2, and -1 minus 3, which is -4 over 2. So why have I spent so much time talking about this? Well, there's a couple good reasons. One of the reasons is you can use this idea to classify things without actually even finding the values. So it's going to be true that if the determinant is negative, your eigenvalues are always going to be the opposite sign. I'm going to say that again. If the determinant of A is negative, then your eigenvalues are opposite sign. Why would that be true? Well, actually, before I say why would that be true, what does that mean? If the eigenvalues are opposite sign, we know we have what? A saddle. So if you ever can just see that the determinant's negative, you can be done as far as classifying. You can say, like, I know I have a saddle. Now, why would that have to be true? Well, check this out. Here's our solutions. You have a number, tau. It could be positive or negative. And you have this square root. And here's what I'm going to point out. The square root is a bigger number than tau in absolute value if 4 delta is positive, if you're adding on something here. Think about it this way. You have a number. You're adding or subtracting a bigger number. Bigger meaning further away from 0. Let me show you 2 examples. If we were doing 7, I'm adding or subtracting a number bigger than 7. Let's say 9. Am I getting positive and negative? If I do 7 plus or minus 9, one's positive and one's negative, right? Because I took a number and I added and subtracted a bigger number. Adding it just makes it more positive, but subtracting it, since it's a bigger number, gets it to be negative. And then dividing by 2, who cares, all right? Or if our number was negative, and you add or subtract a bigger negative number, meaning a more negative number, like -10, you're going to get the same result. -6 minus 10 is more negative, but -6 plus -10 is more negative. -6 minus -10 is positive. So that's what's happening here. If delta happens to be negative, then you have a negative times negative, which is positive, and whatever you've got here is a number that's bigger than tau, because you've got the square root of tau squared plus some stuff, which is bigger than tau. So whenever your determinant's negative, you always get a saddle. And what we'll see later on, we're not going to do it right now, but what we'll see later on is that there's some other analysis you can do on this formula that allows you to completely determine what kind of system you have based on the trace and the determinant. So it's really kind of powerful. And it means you can kind of really ignore a lot of other stuff instead of having to do those calculations. And your teacher definitely does talk about it. I saw that in his notes, he pointed out, and maybe you're not there yet, but in his notes, he points out that if you're finding the eigenvalues, there are 2 things that are true. Thing 1, the eigenvalues add up to the trace. And thing 2, the eigenvalues multiply to the determinant. So if we know that the determinant is negative, oh yeah, look, the eigenvalues have to be opposite signs. Okay, so I know that was kind of a big swerve this way, but it's worthwhile. I keep trying to justify, like, trust me, the things we're doing are worthwhile. They are worthwhile. Yeah. Back to where we were for a minute. Let's say we had, so let's look at a couple other examples. Let's say we had this matrix, and we're going to often start just talking about the matrix, right? I'm going to write down this matrix, 6, -4, -3, 5. And we're all going to be operating under the assumption that, oh, what we really mean here is we have, right, this is really dx dt equals 6x minus 4y, and dy dt equals negative 3x plus 5y. We're not going to write that out because we're all just going to understand that's what we mean. Okay, let's find the eigenvalues. So I'm going to do it the other way. I'm going to say, okay, the trace here is 11. The determinant here is 6 times 5 is 30 minus negative 4 times negative 3 is 30 minus 12, which is 18. This feels like it's not going to be wonderful, right? Sometimes this other method might not be the best. So you should definitely, you should use discretion. If I start trying to do this here, my eigenvalues are going to be trace plus or minus the square root of the trace squared minus 4 times the determinant all over 2. That seems not super great, right? I don't love that. Could we figure out what's going on still? Yeah. So let me ask everybody. Are my eigenvalues going to be positive or negative or maybe one of each? Well, what do we know they're definitely not going to be? They're definitely not going to be both negative because 11 plus some number is going to be positive. What about 11 minus this number? It could be negative, but it could be positive. How could I tell? Well, check this out. If I've got 11, okay, we know 11 plus 11 squared minus 4 times 18 over 2. That's definitely positive. But 11 minus 11 squared minus 4 times 18. Okay, here's where we really have to think about this for a second. Am I subtracting a number that's bigger than 11 or less than 11? It's a good question. So I've got 11 squared. So if I was just taking the square root of 11 squared, it'd be 11. Is the number I'm taking the square root of bigger than 11 squared or smaller than 11 squared? Am I subtracting from it or am I adding to it? Subtracting from it, which means it's smaller than 11 squared. And if the number is smaller than 11 squared, which is 121, so if it's smaller than 121, its square root is going to be bigger or smaller than 11. It's going to be smaller than 11. So this number here is smaller than 11, which means 11 minus it is also positive. Or, which I could have said in yeah, thank you. Also from, yes, smaller. What I could have said from the very get-go is, since the determinant is positive instead of being negative, the eigenvalues have to be the same sign. So when the so I should say I should caveat this with, if the eigenvalues are real and the determinant is positive, the eigenvalues have to be the same sign. But when the determinant is real, the eigenvalues can also be imaginary. So just be careful. So if the determinant is positive, then they're the same sign. And so since the trace is also positive, we know for sure that the eigenvalues are both positive, which means we have a source or an unstable node. And one more example. Notice I didn't actually find the eigenvalues. So you should kind of pay attention to what you're being asked for. Right? If someone says find the eigenvalues, you got to find the eigenvalues. And we totally could have found them here. They're definitely not impossible. If you had actually wanted to find them, 11 plus or minus the square root of 11 squared minus 4 times 18 is 18 times 2, which is 36, times another 2, which is 72. That looks terrible. Why is that not seeming to be what I want it to be? Could I have made a mistake? It's always possible. Oh no, I didn't make a mistake. I'm just adding poorly. 121 minus 72 is 49. 11 plus minus the square root of 49. over 2 is 11 plus or minus 7 over 2, which is 18 over 2 and 4 over 2. So then you can, right? So I'm trying to say in the most roundabout way possible is you have options, right? You can do it the other way, you can do it whichever way. You can actually find the eigenvalues, or if you're just being asked about the behavior, you can be like, well, I can see the eigenvalues are positive. So just think about what you're being asked to do. I don't want you to do more work than you need to is almost always my mantra. Let's look at this last example. Let's say this is our matrix, -3, -1, 1, -6. And we can find the eigenvalues in any which way we want. So we could, let's do it the new way. So our trace here is -3 plus -6, which is -9. And the determinant is -3 times -6 minus -1 times 1, which is 18 plus 1, which is 19. So we already know what's going to happen. Well, maybe I already know what's going to happen for sure. You guys probably can figure it out if you just think about it for a second. So our determinant is positive or negative? Positive, which means the eigenvalues have to be opposite or the same sign. Have to be the same. And the trace is negative. And the eigenvalues have to add up to the trace. So the eigenvalues both have to be the same sign. They both have to be negative. So eigenvalues multiply to this. Eigenvalues add up to this. Oh, they have to be positive. They have to be negative because they added to a negative. Or I could say, since they add to a negative, they could be one of each, negative and positive, or they could both be negative. But since they multiply to a positive, they have to both be negative. And then you could actually find what you want to. The eigenvalues are going to equal -9 plus or minus the square root of -9 squared minus 4 times 1 times 19 all over 2. And this is words. This does not end up being very nice. But again, I'll point out, you can see this and see they're both going to be negative. Because you've got -9 minus something, okay, negative. You've got -9 plus something, and the something you're adding isn't quite as big as 9. It's a square root of 81 minus some stuff, which is a number that's smaller than 81, whose square root is smaller than 9. I'm actually writing out the numbers. It's, let's see, 4 times 19. 19 times 2 is 38. 38 times 2 is 76. So you get -9 plus or minus the square root of 5 all over 2. And it's definitely a negative and another negative. -9 minus root 5 over 2 is certainly negative. -9 plus root 5 is not big enough to overcome the negativeness. So those are both lambda 1 equal to -9 plus root 5 over 2. And lambda 2 equal to -9 minus root 5 over 2. Are both negative, meaning we have a stable, I should really say the origin 0, 0 is a stable node, also known as a sink. And then I made a reference to something that should go back and say real quick. So I just want to point out, and again, this is something that sometimes people don't focus on, but I feel like I should mention it. A linear system of equations doesn't have to have the origin as its only as the equilibrium. You can have a linear system that's not homogeneous. So just as one last quick example here, we're not going to solve this. I'm just going to point out a homogeneous linear system of differential equations looks like what we've been looking at. You've got the derivative of x equal to some 3x minus 4y, and the derivative of y equal to something times x plus something times y. And when you set those both equal to 0, your solution is 0, 0. But there are other linear equations that have different solutions, something like this, a non-homogeneous system. linear system, I should really say. Again, I know last quarter I was looking at this. Tim Lewis, who was teaching it, definitely focused on this a lot. I don't think Rademacher typically does. So here's a non-homogeneous system. dx dt equal to x minus 2, dy dt equal to 4x minus 3y plus 1. And if we set both of those equal to 0, we definitely do not get the origin as the equilibrium point. Here, we're going to get x equal to 2. And if x is 2, we're going to get 8 minus 3y plus 1 equal to 0. So negative 3y is going to equal negative 9. So y is going to equal 3. So that one would have the single equilibrium point of 2, 3. So I just wanted to correct that I did misspeak a little bit earlier. Right? This is still considered a linear system of differential equations because your powers of x and y are just 1, but it's a non-homogeneous system because you have constants in the mix that are not equal to 0. We still treat this very similar to how we treat this. You still would find the system of solutions the same sort of way with a little bit of extra work. You still classify them the same sort of way by looking at the eigenvalues. All right, we will continue on next week.